TCP/IP is fast becoming the de facto data communications protocol of choice for network designers. Its dominance is primarily driven by its use within the Internet. This module is designed to give an overview of the TCP/IP protocol suite and to outline associated processes such as IP routing. This module should be completed before proceeding with the more in-depth studies of the Internet and IP services contained in the other modules on this CD. In the first section of this training module, we will examine the history behind the development of the TCP/IP protocol suite, from its early definition by the US Department of Defense to its dominant use in today's business-critical Internet. We will investigate the regulation of the protocol suite's development and the benefits provided in adopting a layered approach to these developments. In later sections, we will investigate in more detail the components of the Internet protocol, how this can be used to transmit information between computers, and how the transmission control protocol can guarantee a secure end-to-end service for this information transfer. Finally, we will investigate a number of standard application processes that can make use of TCP/IP transmissions. The development of the TCP/IP protocol suite and the Internet go hand in hand. This slide, however, focuses on the main events associated with TCP/IP's development. For more on the development of the Internet, see the associated module on the Internet development. The Internet as we know it today traces its origins back to a Defense Department project in 1969. The subject of the project was wartime digital communications. At that time, the telephone system was about the only theater-scale communications system in use. A major problem had been identified in its design, its dependence on switching stations that could be targeted during an attack. Would it be possible to design a network that could quickly reroute digital traffic around failed nodes? To achieve a working solution, the Defense Advanced Research Projects Agency, DARPA, launched the DARPA Internet Program. The resulting Advanced Research Agency network, ARPANET, went live in 1969. The ARPANET, largely the plaything of academic and military researchers, spent more than a decade in relative obscurity. As Vietnam, Watergate, the oil crisis, and the Iranian hostage crisis rolled over the nation, several Internet research teams proceeded through an evolution of protocols. The idea of open architecture networking was first introduced at DARPA in 1972. The existing Network Control Protocol, NCP, did not have the ability to address networks and hosts further downstream than a destination switch on the ARPANET. Thus, DARPA decided to develop a new version of the protocol which could meet the needs of an open architecture network environment. This protocol would eventually be called the Transmission Control Protocol Internet Protocol, TCP/IP. While NCP tended to act like a device driver, the new protocol would be more like a communications protocol. In 1979, the Internet Control and Configuration Board, ICCB, was formed. Their charter was to provide an oversight function for the design and development of protocols, including TCP/IP, within the Internet. In 1983, this was renamed the Internet Activities Board, IAB, and the Internet Engineering Task Force, IETF, was added in 1984. Development on TCP/IP continued after its initial definition. The most common versions of TCP and IP, in fact, date back to 1981. In 1982, the Department of Defense declared that TCP/IP would become the new standard ARPANET protocol suite, and the official cutover occurred on January 1, 1983. An even bigger boost for TCP/IP came from the University of California at Berkeley in 1983, when TCP/IP was bundled with their version of Unix. Domain naming via use of domain name servers was introduced in 1987. Until then, host names were mapped to IP addresses using static tables, but the Internet's exponential growth had made this practice infeasible. In the early 90s, the first address exhaustion crisis hit the Internet technical community. The present solution, classless interdomain routing, CIDR, will sustain the Internet for a few more years by making more efficient use of IP's existing address space. For a more lasting solution, IETF is looking at IP version 6 and its larger address space, but CIDR is here to stay. In the late 1980s, many large corporations found themselves thrust into a multi-vendor computing and communications environment. Such an environment was brought about primarily by the autonomy of workgroups in the purchase of local area networks, LANs, and associated applications, but also due to mergers and acquisitions. As users began to need access to the resources of other workgroups, the requirement to interconnect LANs on a company-wide basis emerged. None of the major computer vendors, for example IBM and DEC, offered a model for communications that supported connectivity and interoperability among many different vendors' equipment. Hence, network managers were required to operate multiple computer networks, each with their networking protocols. Corporate information systems managers began to search for a model for multi-vendor interconnection, and soon discovered the Internet model and its foundation, the TCPIP protocol suite. They began building structures based on the Internet model, using the protocols developed within that environment. Hence, networks today are converging on a model built around the Internet and the TCPIP protocol suite in particular. This networking trend towards everything TCP/IP has had a dramatic impact on the internetworking marketplace. Traditional multi-application networks running on multiple protocols such as IBM SNA and Nortel IPX are migrating to operate on an all TCP/IP environment. In a recent Forrester survey of 50 top US companies, there has been a dramatic increase in the use of TCP/IP. The number of companies reporting networks with more than 50% of applications on IP has risen from 18% in 1996 to 82% in 1998, and this trend is set to continue. The convergence of data networking towards exclusive use of TCP/IP is only the start. Recently, the press and TV have carried article after article on the emergence of IP's support for traditional circuit switch services such as video and voice. For example, Microsoft now ships desktop video conferencing over IP as part of its Windows 98 OS package. Whole new companies are starting up based on the ability of IP to carry traditional voice cheaper than existing voice networks. An understanding of such an important and market-shaping protocol suite is now essential for anyone involved in telecommunications. The Internet Architecture Board, IAB, was formed in 1983 to coordinate and guide the design of internetworking protocols and development of the Internet. The board is responsible for publishing all protocols and standards and initiates the procedures by which all standards are developed. The IAB is divided into various areas responsible for a range of topics to do with researching and development. The research is covered by the Internet Research Task Force, IRTF. Developments are controlled by the Internet Engineering Task Force, IETF. The IETF is split into various work groups to study different aspects of the TCP/IP protocol suite. Request for comments, or RFCs, are documents that define all protocols, standards, assigned numbering schemes, and general information related to the TCP/IP protocol suite and the Internet in general. There are currently over 2,000 RFC documents that are available via postal mail, electronic mail, file transfer, and via the web from the Network Information Center, NIC, operated by the IAB. RFCs are numbered sequentially as they are published. Draft RFCs are called appropriately Internet drafts. As an RFC undergoes revision, the newer version is given a new RFC number and supersedes previous versions. For example, RFC 793 describes the Transmission Control Protocol, TCP. This RFC supersedes the earlier versions of TCP numbered 761 and 675. Draft RFCs can be submitted by anyone. Vendors, users, and service providers lead the working groups within the IETF. As a quick aside, a lot of good technical humor can be found in any draft RFC dated the 1st of April. In the early 1980s, the International Standards Organization, ISO, generated a 7-layer model into which existing and new standards could be added. The 7-layer model is an example of a stacked architecture. The idea is based around a modular approach. If you have a standard defining a protocol that operates at one layer and is designed to carry out certain functions, then it is feasible to have many layers, the total of which provides for all the connection and communications elements required. To add more flexibility to the model, each layer is designed to operate independently of the others. Should any change need to be made to the network, that layer of the technology can be replaced without impacting on the operation of the existing upper and lower layers. The US Department of Defense, DoD, originally defined the TCP/IP protocol within their reference model used on ARPANET. The DoD model is a 4-layer model. The comparison of the two models shows that the two are similar in concept, but have a different number of layers with different names. While similar things happen at similar places, the specification on how these things happen are different. This leads to a very different suite of protocols for the DoD model. As already discussed, each layer of the stacked architecture operates independently of the others. This is achieved using a method referred to as encapsulation. Each layer communicates to its adjacent layers using well-defined service access points, or SAPs. Any layered protocol can be developed independently of adjacent layers as long as its data is received or sent via these SAPs. The layer receiving data from the layer above will process the data, add its own protocol header, and transfer the data block to the layer below. The layer below will simply treat the data as a block. It will not try to understand its meaning. This process is undertaken at all layers by the sending device. At the receiving device, the reverse happens. When data arrives, the first layer processes its peer header and then passes the data to the layer above, which carries out the same action. When the TCP/IP protocol suite was first developed, it was as one large protocol that incorporated all facilities. Since 1979, the functionality has been split up and a 4-layer architecture has been deployed. The network access layer is the lowest layer and is dependent on the type of networks that a device is connected to. The TCP/IP protocol suite does not define any particular network access protocols, but there are RFCs recommending how TCP/IP uses Ethernet, FDDI, frame relay, X25, and even ATM. The layer is responsible for transferring data from one device on a network to any other on the same network, e.g. from a host to a router. The Internet layer is the layer at which the Internet protocol, IP, resides. The function of this layer is to deliver data from any host on the internetwork to any other host, regardless of the network or the destination. It is at this layer that routing function occurs, and so a router may not necessarily implement any higher layers. There are several protocols that can be implemented at this layer that assist IP to deliver data in the best possible way. The host-to-host layer is the end-to-end transport layer. The Transmission Control Protocol, TCP, resides at this layer to provide reliable transport to and from applications implemented at the hosts. There is an alternative protocol also at this layer called the User Datagram Protocol, UDP, which provides unreliable transport. Within the TCP/IP protocol suite, applications are referred to as processes, whether or not they are designed to be used by humans or other programs. Examples of processes can be found to provide support for transferring files, email, and network management. In the next section of this training module, we will cover the details of the Internet protocol. On completion of this section, the participant will have an understanding of the IP packet structure, its control header, the format of the IP address, and how to apply masking to these addresses to achieve sub-networking. We will also investigate the future direction of IP with the planned introduction of IP version 6. The Internet Protocol, IP, provides a connectionless OSI network layer service. IP implements a datagram network. Datagrams, sometimes referred to as packets, are routed on a packet-by-packet basis from IP node to IP node. For each link and each node, IP does its best to deliver the datagram. To do this, IP defines mechanisms for datagram fragmentation and reassembly, hierarchically structuring the IP address, controlling packet lifetime in the network, and verifying the integrity of the IP header. As a connectionless protocol, IP handles each datagram individually, which means that packets can be dynamically routed around network trouble spots. Hosts do not need to establish a logical connection before exchanging IP datagrams. IP service is unreliable. It is appropriate to take a moment and reflect on the word unreliable. In an OSI context, the term unreliable refers to the fact that IP does not sequence or acknowledge datagrams, nor does it provide bit error detection or correction for datagram. There is no guarantee of delivery. If a datagram is lost, there is no indication to the end host that this has happened. It is left to the upper layers to resolve the issue. A number of adjunct protocols are associated with IP. The Routing Information Protocol, RIP, and Open Shortest Path First Protocol, OSFP, are used to determine the routing tables for IP datagrams within a network. RIP is the older of the two protocols and is currently being phased out by OSPF. The Border Gateway Protocol, BGP, is used for routing IP between networks and is particularly important in the Internet. The Internet Control Message Protocol, ICMP, defines messages used for the exchange of error and information used for diagnostic purposes. A number of protocols are defined to assist in IP address allocation and resolution. These are particularly important in building real internetworks using IP. Each will be covered in more detail in future slides. Every element of data sent by one host to another host contains an IP header. The current version of IP used in networks today is version 4. The next version of IP will be version 6. The new version of IP will provide a number of new features, not least the support for 16-byte addressing rather than the current 4-byte. The version of IP used by the host is included in the header in the version field. The header is usually a 20-byte block of control information. The header can be up to 60 bytes of information if the IP options are used. These are usually only used for network engineering. The length of the header is indicated by the Internet Header Length, IHL field, which is normally set to 5. A number of critical control fields are included in the header. The Type of Service, TOS field, allows the host to request that a route be used that has particular characteristics, such as low delay, high throughput, or high availability. This field is currently being modified to allow support for the new IETF class of service proposal called Differentiated Service, or DIFSER. The Total Length field provides a byte count of the total IP datagram, including the IP header. The Identification, More Fragments flag, MF, and Offset fields are all used in datagram fragmentation. This process is explained on the next slide. The DF, Don't Fragment flag, can be used to indicate that a datagram must not be fragmented even if the network requires it. If this happens, the datagram is dropped and an error message generated. The Time to Live, TTL field, is used to ensure that datagrams do not loop endlessly through a router network. When a datagram is generated by a host, a value is placed in this field, usually 32, 64, or 255. Every router that receives this datagram decrements this field by 1. Should a router receive a datagram, decrement this field by 1, and the count equals 0, then the datagram is considered lost and is discarded. The protocol field provides a pointer as to which higher layer protocol the data field should be passed to next. Common values are 6 for TCP, 17 for UDP, and 1 for ICMP. The header checksum is a very simple checksum performed on the header only. The checking of data is presumed to be the responsibility of higher layers. When a router receives a datagram, it will only validate the header for errors to ensure that it is routing the datagram using valid addressing. The source and destination IP address gives the addresses of the receiving and sending host. The IP address structure is discussed in detail in future slides. The size of IP datagrams may be up to 64,000 bytes in length. IP supports a packet fragmentation and reassembly capability, since the size of an actual IP transmission is limited by the underlying physical networks to which the host systems are attached and any intervening subnetworks. Assume a host based on an Ethernet network with a maximum frame size of 1500 bytes transmits a single large IP datagram to a host over an IP network with a maximum IP datagram size of 1024 bytes. The IP datagram from the Ethernet won't fit. Fragmentation is an essential service that all routers and hosts support. The router always fragments, and the recipient host always reassembles. Note that a router never reassembles the datagram it is routing. The recipient host needs 3 pieces of information to reassemble the datagram correctly. The first piece of information is that all the fragments belong to the same original datagram. This is achieved by using the identifier field in the IP header. The second piece of information the host needs is to identify that all the fragments have been received. This is achieved by setting the more bit indicator in the IP header. Only once the last fragment, with more bit set to 0, have all the fragments been received. Finally, the host needs information that all the fragments can be reassembled in the right order. This is achieved using the offset field in the IP header. This allows the host to reorder the fragments should they arrive in the wrong order. The first fragment contains 1024 bytes of user traffic and a 20-byte header. Hence, the total length field is set to 1044. The offset is set to 0, indicating it is the first fragment. The more fragments bit is set to 0 to indicate that more fragments are still to come. The second fragment contains the remaining 476 bytes of data, so the total length is set to 496 bytes. The offset is set to 1024 to indicate that this is the second fragment, and the more fragment bit is set to 1 to indicate that this is the last fragment. In both fragments, the identifier field is set to the same number as that contained in the original datagram. With this information, the destination host can reassemble the fragments. The Arabs invented the decimal system back in the 9th century. Since then, people have loved to count using this system. However, all digital computers represent data as a collection of bits. A bit is the smallest possible unit of information. It can be in one of 2 states, off or on, 0 or 1. The meaning of the bit, which can represent almost anything, is unimportant at this point. The thing to remember is that all computer data, a text file on disk, a program in memory, a packet on a network, is ultimately a collection of bits. The binary system is the representation of numbers using 2 states, or base 2. Simple binary numbers can easily be represented using 1s and 0s, but large binary numbers are hard to write. Computer scientists often write them using hexadecimal or base 16 notation. This is often called hex. When considering IP addresses, it is important that you can understand hex notation and convert from binary to hex to decimal. A common and convenient grouping of bits is the byte or octet, composed of 8 bits. Obviously, if a byte has 256 possible states, its exact state can be represented by a number from 1 to 256. However, since 0 is a very important number, a byte is more typically represented by a number from 0 to 255. This is very common, and with bit pattern 00000000 representing 0, and bit pattern 11111111 representing 255. The numbers matching these two patterns, and everything in between, can be computed by assigning a weight to each bit, multiplying each bit's value, 0 or 1, by its weight, and then adding the totals. For example, here's how 250 is represented in binary: 11111010. If hexadecimal is the representation of numbers using base 16, how do you represent numbers from 10 to 15? You use letters A through F. This is important as it allows you to represent binary in shorthand. The binary number 11111010 can simply be written as FA. Conversion to decimal can now be achieved easily using multiples of 16. FA is equal to 16 times 15 plus 10 times 1, which equals decimal 250. Each device attached to any IP-based network must be given a unique address. These must be assigned at configuration time or dynamically at boot up. These addresses are carried in the header of all information transmitted over the network to identify the source and destination computers. The current IP version, IPv4, defines 32-bit, 4-byte addresses, which permit over 4 billion computers or hosts to attach to a single internetwork. IP addresses are represented in a format known as dotted decimal, where each byte is represented by its decimal equivalent, and the four numbers are separated by a dot. With 8 bits, you can represent numbers between 0 and 255. Therefore, the IP address, represented in binary as 100000000, 01000011, 001000110, 0001011, is written and spoken in the easier-to-remember dotted decimal notation as 128.67.38.23. The IP address space is flat with a two-part division. Each IP address has two components, a network identifier, or net ID, and a host identifier, host ID. The net ID identifies the specific subnetwork to which the computer is attached. The host ID uniquely identifies a particular computer within that subnetwork. To make sure that there is never any duplication of network numbers in the Internet, all networks must obtain an official net ID from the Internet-assigned number authority if they wish to connect their network to the Internet. The allocation of address bits between the net ID and host ID will determine how many subnetworks can be defined and how many computers can be attached to a particular network. In order for IP addresses to be relevant to the type of network that they're associated with, the IAB developed classes of address that are chosen depending on the size of the network. To strike a balance between efficient use of the address space and the needs of different networks, 5 classes of address were defined, designated Class A through Class E. The 3 main classes of interest to us are A, B, and C. The essential difference between these classes is the different sizes of the net ID and host ID fields. Class A addresses, indicated by a 0 in the first bit of the address, have an 8-bit net ID and a 24-bit host ID. There are only 126 possible Class A addresses, as the net ID can only be 1 to 127. Thus, a Class A address is intended for use in very large networks, since the 24-bit host ID can uniquely identify over 4 million computers. Most of the possible Class A addresses have already been allocated. Class B addresses, indicated by a 1 followed by a 0 in the first 2 bits of the address, have a 16-bit net ID and a 16-bit host ID. Subnetworks can support up to 65,534 computers, and there are 16,382 possible addresses. Again, we can see that the restriction of the first 2 bits to 1 and 0 respectively limits the total number of Class B networks to 16,382. The Class B address is intended for moderate-sized networks. Well over 2/3 of the possible Class B addresses have now been allocated. Class C addresses, defined by 2 1s followed by a 0 in the first 3 bits of the address, are intended for small subnets. Class C addresses have a 24-bit net ID and an 8-bit host ID, yielding over 2 million possible addresses. Each network can support up to 254 computers. Most companies who now request a new Internet address are provided Class C addresses. If they require support for more than 254 hosts, then they are provided multiple Class C addresses. Only when they need more than 16 Class C addresses are they given a Class B address. No organization, when it secures a Class A or B address, plans to deploy a single LAN with over 16 million for Class A or 65,000 for Class B hosts. Instead, the organization needs to further allocate the address space to regions, divisions, departments, and so forth. The mechanism to do this is called the subnet mask. A mask is an electronic filter used to extract particular portions of a data field. A subnet mask is used to extract the net ID from the IP address. The subnet mask uses the logical AND operation. Each bit in the IP address is ANDed to the corresponding bit in the subnet mask. If both bits are 1, the result is 1. Any other combination results in 0. This is the equivalent of mathematical addition. The subnet mask has the effect of clearing, i.e. setting to 0, all of the bits corresponding to the host ID. In the example shown, the IP address 150.128.110.1 is ANDed with the subnet mask 255.255.0.0. The result of this process is the new value 150.128.0.0. We effectively zeroed out the host ID, leaving only the net ID. By using this mechanism, an organization can break free of the strict rules of IP address classes and allocate addresses from the pool as needed. In effect, this is done by borrowing some of the host ID bits and making them part of the net ID. Consider the following example. Assume that Company X has been assigned Class B address 128.56.0.0 and wishes to establish a number of small networks, each with less than 255 hosts. The company would like to treat their Class B address as a collection of Class C addresses. To accomplish this, the company partitions the address by telling each department which value to use in the third byte of the address and to use the subnet mask 255.255.255.0. Now, Finance Department will use 128.56.34.0, and Sales will use 128.56.22.0. The subnet mask is used to find the net IDs, which are now 128.56.34 and 128.56.22 respectively. This will greatly simplify the task of the routers. Rather than having to learn about 16,000 hosts, the router only needs to find 254 subnets. Back in the mid-1990s, with a new network being connected to the Internet every 30 minutes, the Internet was faced with 2 critical problems. It was running out of IP addresses, and the routers in its backbone were running out of capacity in their global routing tables. Because Internet addresses were generally only assigned within the 3 class sizes, there were a lot of wasted addresses. For example, if you needed 100 addresses, you would be assigned the smallest address, Class C, but that still meant 154 unused addresses. The overall result was that while the Internet was running out of unassigned addresses, only 3% of the assigned addresses were actually being used. A related problem was the sheer size of the Internet global routing tables. As the number of networks on the Internet increased, so did the number of routes. A few years back, it was forecast that the global backbone Internet routers were fast approaching their limit on the number of routes they could support. Even using the latest router technology, the maximum theoretical routing table size is approximately 60,000 routing table entries. If nothing was done, the global routing tables would have reached capacity by mid-1994, and all Internet growth would be halted. Classless interdomain routing, CIDR, is a replacement for the old process of assigning class A, B, and C addresses with a generalized network prefix. Instead of being limited to network identifiers or prefixes of 8, 16, or 24 bits, CIDR currently uses prefixes anywhere from 19 to 27 bits. Thus, blocks of addresses can be assigned for networks as small as 32 hosts up to networks with over 500,000 hosts, allowing for address assignments that much more closely fit an organization's specific needs. A CIDR address includes the standard 32-bit IP address and also information on how many bits are used for the network prefix. For example, in the CIDR address 206.13.01.48/25, the /25 indicates the first 25 bits are used to identify the unique network, leaving the remaining bits to identify the specific host. The CIDR addressing scheme also enables route aggregation, in which a single high-level route entry can represent many lower-level routes in the global routing tables. The scheme is similar to the telephone network, where the network is set up in a hierarchical structure. A high-level backbone network node only looks at the area code information, and then routes the call to the specific backbone node responsible for that area code. The receiving node then looks at the phone number prefix and routes the call to its subtending network node responsible for that prefix, and so on. The backbone network nodes only need routing table entries for area codes, each representing huge blocks of individual telephone numbers, not for every unique telephone number. Currently, big blocks of addresses are assigned to the large Internet service providers, ISPs, who then reallocate portions of their address blocks to their customers. For example, an ISP might be assigned a CIDR address block with a prefix of /15, equivalent to 512 Class C addresses or 131,072 host addresses, and typically assigns its customers CIDR addresses with prefixes ranging from /27 to /19. These customers, who may be smaller ISPs themselves, in turn reallocate portions of their address block to their users and/or customers. However, in the global routing tables, all these different networks and hosts can be represented by the single Internet route entry. In this way, the growth in the number of routing table entries at each level in the network hierarchy has been significantly reduced. Currently, the global routing tables have approximately 40,000 entries. It is worth spending a moment to examine where IP address assignments come from and how they are assigned within an IP-based internetwork. First off, anyone can select their own IP address if they are on a private network. However, there is almost nothing to be gained by doing this. If you build a private IP network with a random IP address, what happens if you later decide to connect to the Internet? Invariably, you will have to renumber your computers. When attaching to the Internet, as already stated, net IDs are assigned by the Internet Assigned Number Authority, IANA. The IANA assigns net IDs to individual organizations or to Internet service providers who in turn assign them to their customers. With a few exceptions, the recommended source for an address assignment today is the customer's ISP. Under this scenario, the customers are only renting the address, and if they change ISPs, it is strongly recommended that they get a new address from their new ISP and renumber all their network devices. Host IDs are assigned locally by an address administrator. This function is essential to ensure that duplicate addresses are not assigned within an organization, just as IANA ensures that duplicate net IDs are not assigned. IP addresses themselves are not assigned on a per-device basis, as the name host ID might imply, but on a per-port or attachment basis. This means that some equipment is administratively part of multiple networks and has multiple IP addresses. In this simple network, Site 1, the LAN on the left, has an assigned Class C net ID 199.182.20. The two PCs and the router on the LAN have been assigned host IDs 17, 5, and 100 respectively. This LAN is attached to some wide area network or WAN service provider, which has an assigned Class B net ID 142.100. The WAN has assigned the Site 1 LAN router a host ID of 81.54, so that the router's WAN port has an IP address of 142.100.81.54. Hence, the router in effect has two IP addresses, one for each of its physical ports. A similar scenario can be found at Site 2, where a customer's host system is directly attached to their own router. Again, the router has two IP addresses because it is part of two different systems. Finally, the host at Site 3 has a host ID directly assigned from the WAN service provider's address space. This represents a host that is actually a part of the WAN. In the connectionless datagram environment of IP, each host and node acts autonomously. Datagram delivery is on a best efforts basis. Everything functions just fine as long as the network is working correctly. But what happens when something goes wrong with the network? Internet Control Message Protocol, or ICMP, is an IP-to-IP communications protocol to provide a solution to this problem. ICMP messages, delivered in IP packets, are used for out-of-band messages related to network operation or misoperation. Of course, since ICMP uses IP, ICMP packet delivery is unreliable, so hosts can't count on receiving ICMP packets for any network problem. ICMP announces network errors, such as a host or entire portion of the network being unreachable due to some type of failure. A TCP or UDP packet directed at a TCP port number with no receiver attached is also reported via ICMP. Note, TCP port numbers will be explained later in this module. ICMP indicates network congestion. When a router begins buffering too many packets, due to an inability to transmit them as fast as they are being received, it will generate ICMP source quench messages. Directed at the sender, these messages should cause the rate of packet transmission to be slowed. Of course, generating too many source quench messages would cause even more network congestion, so they are used sparingly. ICMP can provide troubleshooting features. ICMP supports an echo function, which just sends a packet on a round trip between two hosts. Ping, a common network management tool, is based on this feature. Ping will transmit a series of packets, measuring average round-trip times and computing loss percentages. ICMP can announce datagram timeouts. If an IP packet's TTL field drops to 0, the router discarding the packet will generate an ICMP packet announcing this fact. Traceroute is a tool which maps network routes by sending packets with small TTL values and watching the ICMP timeout announcements. IP version 4 has served the Internet community well, but it has limited address space and is causing problems as more and more hosts connect to the Internet. As already indicated, a solution was developed with the creation of CIDR, which allocated Class C addresses as variable-size blocks. This leaves addresses free for other users. Still, CIDR only buys time. The IETF began working on an IP update in 1991. What was finally hammered out was IP version 6. often known by its project name of IP Next Generation, or IPNG. The protocol was officially entered into the standards track in 1995. The most important feature of IP version 6 is its longer address space. It is 16 bytes long, compared to 4 bytes in IP version 4. That will provide enough address space to assign an IP address to every person and every conceivable device on the planet. Imagine your home entertainment system has an IP address. From your office, you could send a command to have it record the latest episode of your favorite television show. The addition of 3 types of addresses, unicast, anycast, and multicast, improve the support for multicast in IP networks. The IP version 6 header has been significantly modified compared to the IP version 4 header. Some IP version 4 fields have been dropped or made optional to reduce the common case processing cost of packet handling and to limit the bandwidth cost of the IP version 6 header. Another important feature of IP version 6 is support for multimedia. A new capability is added to enable the labeling of packets belonging to particular traffic flows for which the sender requests special handling, such as non-default quality of service or real-time service. Despite the necessity of IP version 6's development and its almost guaranteed success, the transition from IP version 4 to IP version 6 will not occur quickly nor painlessly. The single fact that there are millions of hosts on the public internet alone that need to be upgraded suggests that almost nothing can move quickly. The transition to IP version 6 will start with the network infrastructure, meaning the routers, domain name servers, DNS, and routing protocols. It is clear there will be IP version 6, IP version 4 coexistence for years to come. Remember, IP version 6 supports IP version 4 numbers, so servers can be upgraded while clients remain on IP version 4.